Hello guys, welcome back again to BerTronix TV. In this video, we will talk about the RMS. What is meant by the root mean square, where the heck it came from, and that is the one that I will try to give an answer. Let's start with the concept of how we can measure the energy being delivered to the load. In electrical circuit, this is the effective or average power being dissipated to the load, and let's say the load is a resistor. And as we all know, the formula for the power is the product of the current and voltage. In terms of voltage and resistance, we have power B squared all over R. And in terms of current and resistance, we have power equal to the I squared R. Then the effective power can be derived from the summation of instantaneous power and getting its average value. We can also use the integral form to get the total average power. Let us have an example. In DC circuit wherein a constant voltage is being applied to the resistive load, therefore we will have also a constant current. If I sample the power, that means taking the product of the voltage and the current at different points, and then take the average of those samples, that will give us the effective power delivered to the load using the summation formula. We will call each sample as the instantaneous power. With a given circuit, let us use 1 volt and 2 ohm resistor. And say we have 4 samples of power that is 0.5 watts, so that it will be 2 watts by 4 equal to 0.5 watts. You will observe that in DC, the instantaneous power is the same as the average power, which makes sense because we have a constant voltage and current at any point of our samples. So in DC, we just need to have the product of the voltage and the current. Then we know that this is the effective power delivered to the load. In terms of voltage and resistive load, we use the B squared over R. And with the current and load, we will use the I squared R. So it is easy in DC. What about if I have a voltage or current that changes with time? In here, we will use the sinusoidal example because it is the common type of the AC input we use in electrical circuits. You will now observe that in the case of AC, the instantaneous power will have different values with respect to the time or the point of sampling. Increasing the number of samples will get us closer and closer to the average value of our waveform, which is the area under the curve. Please do note that with the summation formula, it is only an approximation with error, getting less and less as we increase the value of samples. To get rid of approximation, we can use the integral form for the total average power. Let us take again our sample circuit using the same resistor load but with DC and AC input. The goal is to look for the average AC power that will deliver the same amount of average DC power to the load. In here, we will equate the two power, and as we observe, the instantaneous power for the DC turns to be equal to the average power, so that I will just use one sample point for a DC as my effective power and equate it to the average AC power. Let's start with the voltage and the load, and in here you will see that the resistor will be cancelled from the equation. Now we will have our effective voltage by taking the root of the right side of the equation. Take a look and examine the right side of the equation, and you will observe that this is the very definition of the root mean square voltage. That is taking the root of the mean of the squared voltage samples. Hence, the word root mean square is literally the mathematical definition of the formula itself. Also shown in here is the integral form of the RMS voltage. Same goes with the effective DC power using the I squared formula. By equating it to the average AC power, the resistor will be cancelled from the equation. Now we will have our effective current by taking the root of the right side of the equation. And this will result to the right side of the equation to be the very definition again of the RMS current. that is taking the root of the mean of the squared current samples. Now let us use our derived formulas for solving the sinusoidal RMS voltage and current. Let's start with the input voltage equivalent to B peak sine omega t. Then taking the BRMS, which is equal to the root of 1 by t, integral from 0 to t of the squared input voltage into sine squared omega t times dt. We will use the half angle equivalent of sine squared omega t for us to evaluate the integral more easily. Remember that sine squared theta is equal to 1 less cosine 2 theta all over 2. Using our half angle formula to our sine squared omega t, we will now have this right side of equation. We will evaluate the integral by two parts, one consisting the constant term 1/2 and the other that contains sinusoidal term cosine 2 omega t all over 2. The first integral then will be the integral from 0 to t of 1/2 into dt, that is nothing but a t over 2. And then the other term, as we know, that getting the integral of a cosine function over a one whole cycle is equal to 0. So that the remaining term will only be the root of the b peak squared by t into t by 2. T will be cancelled and we will be left by the root of the b peak squared by 2. Therefore, the final equation for the BRMS of the sinusoidal waveform will be the b peak by square root of 2. This is the formula for the BRMS of a sinusoidal waveform. The same procedure will be taken when you want to derive the RMS value for the current. But for your reference, I included here in the video the derivation for the sinusoidal RMS current. Please take note that this formula is only applicable with the sinusoidal input. Here are the other common AC waveform and their effective RMS values. We have the square wave, triangular, sawtooth, and a pulse with a duty cycle. So guys, that's all for the RMS. Before we end this video, here are the key points that we need to remember. First, the RMS value is the effective AC equivalent of DC that will deliver the same amount of power dissipated to the load. Second, we realize that to derive the RMS value, we should start from the average power analysis. And third, we observe that the root mean square is literally the mathematical definition of the formula itself. Okay guys, that's all for this video and thank you for your support to BerTronix TV. Remember, electronics is made easy with ECE. Bye!